Welcome, ladies and gentlemen, to 6.2, which is entitled Circular Motion. Basically, when you go in a circle or an object goes in a circle, how does that work from a physics standpoint? We've all been in a car, and that car has been going around in a circle. Some of us have maybe even been on roller coasters. Maybe you've been on the Gravitron, or you've seen something like this, or that ball of death where people going around. And there's a difference between centripetal force and centrifugal force. We're going to talk about those. And here's our objectives today. Why is an object moving in a circle at a constant speed? Accelerating. These two words should be oxymorons to you by now. There's no way you can move at a constant speed but accelerate. Today I'm going to show you how to do that. Number two, how does the centripetal acceleration depend on an object's velocity and radius of motion? So just to get everything started here, I have a couple of videos that I have found on YouTube that I wanted to start this with. The first one, of course it comes from Russia. There's a couple guys on a carousel, and they get the bright idea to power this thing with a scooter.
Warte doch. Leg doch erstmal hin.
Was du hast drauf. Hast du schon mal gefühlt, was auf der Stelle steht? Hurensohn! So, jetzt. Warte, dreh! Halt Start! Nein!
Yeah, get rid of that cigarette, sir. You don't want to be smoking that. Now, this is about to get into Newton's first law. Objects in motion stay in motion in a straight line unless acted upon by an outside force. If you watch his head's going to tell the whole story. Keep your eyes on his head. Your neck can only support about 10 pounds of force. When your head gets whipped around in a circle like that, your neck can't take it. And you watch his head start going backwards, he loses it. Head's in, down. There it goes. He's going to move in a straight line. I mean, there's inertia taking over. The moment he's outside of the rails, he moves in a perfectly tangential straight line. The next one I wanted to watch is an F-18 tourist. You can go, this is one of my dreams, is to go on an F-18 and take some really hard corners.
If you're ready for a big pull, we are going to do an Immelman, which is basically pulling right up through the inverted to the vertical to the inverted. Yep. Ready to go?
I am ready.
All right, take a deep breath.
Okay.
Flex your legs, up we go. Oh. 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 That's the Immelman.
Steve is unconscious right now because your body wants to go straight, but the thing that you're in is turning and you have to go with it. So actually the blood in your body goes down to your feet because it really wants to go straight, but your body moves away from it, and so you pass out. They call this G-LOC, or it stands for gravitational loss of consciousness. And they train fighter pilots on how to deal with that stuff. You'll wake up as soon as the blood gets back up there.
Yes, I am. Sorry.
No problem.
Wow. I went nowhere there for a while.
Yeah, I took a little bit of a nap. That's all right. That happens on the Immelman quite frequently.
Wow.
We'll watch one more of him.
All right, 450 knots. Looking pretty
Well, they're going to turn.
Aircraft looking good. Here we go. Take a deep breath. Flex your legs. Here's the burners.
They say flex your legs because they're turning. Blood wants to go straight, so it's getting spun to the bottom of his body, kind of like a centrifuge. And if he can't force it up into his brain, nighty-night. Well, hopefully the blood comes back up to his head, and then he wakes back up.
Get back with me.
Maybe. Circular motion. It kind of stems from, like I said, Newton's first law. Objects in motion stay in motion in a straight line. So if you're traveling in a straight line, you'll continue to travel in a straight line until you have some force that turns you. Now, if you want to turn in a circle, there has to continually be a force on you this way to keep pushing you in a circle. Your book talks about, what if I put like a circle on the ground and you were to roll like a basketball? And we roll the basketball towards us, how would we keep this basketball rolling in a circle? You'd have to continually poke it to keep changing its direction always. And this is called the centripetal force. The centripetal force is what turns an object. And I call it the little c. It's the force it takes to turn an object. Now you might say to yourself, there's a couple things that affect how hard you have to push to make something turn. It depends on how big the object is. The mass of the object. It depends on how tight of a circle. The smaller the circle, the harder you have to push. And it also depends on how fast you're going. The faster you want to go, the more force you need. Here's how we find the centripetal force. There's an equation that we're going to use. It's a brand new one. Centripetal acceleration, it's velocity squared divided by the radius. Centripetal acceleration, we talked about, one of our goals today was, can you be moving around this circle at a constant speed but accelerating? And the answer is yes. If you think back to Newton's second law, if there is a net force on something, then it accelerates in the direction of that net force. Here we go. There's a centripetal force acting on an object as it turns that corner. So that means that it has to accelerate in the direction of that. And that inward acceleration we call the centripetal acceleration. So that's kind of where that comes from. And what you do, you substitute that in to F equals ma. So the centripetal force is mass times centripetal acceleration. So you take this guy right here, plug him in right there, and you end up with the centripetal force is equal to mass velocity squared divided by the radius. And there it comes back to what we had just talked about up here, the three things it depends on. It depends on your mass, depends on how fast you want to go around the corner, and it depends on the radius. So here's our first example of this. It says a 13-gram rubber stopper is attached to a string. The stopper is swung in a horizontal circle above your head, making 1 revolution in 1.18 seconds. Find out how much tension's in this force, in this string in the stopper. So I'll just make a picture. Here's my stopper. The tension. The tension is actually the force that's turning our stopper. If we were to cut this rope, we just cut it right here, this thing would continue out in a straight line. But because the rope exists, that's what's providing the force to turn it, and that's the centripetal force. The centripetal force, mv squared over r. That's the tension. So the mass of the stopper, I want to make sure that I do it in kilograms. So this is 13 grams, so I want to go 0.013 kilograms. The radius of the thing is 0.93, because that's the distance of the string. Now the velocity, that's going to be tricky. The velocity is going to be the distance divided by the time. The distance this thing travels is a circle, So the distance is going to be around a circle, which is the circumference, 2 pi r, and how much time it takes to get around it. So 2 pi, and the radius was 0.93 over the time. It does 1 revolution in 1.18 seconds. So now I can find the velocity of my stopper, and then I just plug it into there. So 2 pi times 0.93 divided by 1.18, and that equals 4.95. And then I'm going to square that number, 4.95 squared times 0.013 divided by 0.93. And I get 0.343. So that's how much force is in this string right here. Let me give you another prime example of why it's good to calculate the centripetal force. Oh, actually, I think I'll save that for another lecture. The last example, it's got a car turning in a circle. You saw that picture we had of Marge and Homer going around a corner. So here's an above view of a car going around a corner. Here's my corner. Here's my car. Now, I talked to you before that there's a force that turns the corner, the centripetal force. When I was a kid on the bus, when the bus used to turn a corner, people inside the bus, like here's a person, as you go around the corner, you get slung to the outside, and then we call that the centrifugal force. It's a fake force. All it is inertia. You're wanting to travel straight, but then the car goes out from underneath you, which gives you this illusion that you're being sucked to the outside of your car, but in reality, you're not. You're just traveling in a straight line. So there's a car going around this corner at 22 meters per second. It's a 56 meter radius. Find the car's centripetal acceleration. Okay, so the centripetal acceleration is velocity squared over the radius. So this is actually not that bad. This one's nice. 22 squared over 56. So 22 squared divided by 56. 22 squared divided by 56 comes out to 8.6 meters per second squared. Okay, what minimum coefficient of static friction? It turns out it's actually friction that's turning this car. Imagine if you're in the middle of a corner and we turn friction off. You're going to go skidding off the road. And that's what happens, like when you get going around a corner and you lock your brakes, you no longer have that friction and you go skidding off the side of the road. You hit black ice. Friction is what is actually turning you while you're going around the corner. And that's where you start with this one. Friction is what turns you. This is so often the case. A person running around a track, you're relying pretty heavily on friction to make that corner. So whenever you get a problem where you're turning a corner and it's friction, this is where you start, right here. The force of friction equals the centripetal force. And the force of friction is always the coefficient times the normal force. The centripetal force is mv squared over r. Now, because we're on flat ground, the normal force is going to be equal to gravity. And we also know that gravity is just 9.8 times the mass. So the coefficient of friction, 9.80 times the mass m, that's what gravity is. And gravity, in that case, makes it the normal force, and then that times the coefficient is friction. Now watch this. You might be thinking to yourself, I can't do this problem because they don't tell me the mass of the car. It doesn't matter because there's an m on both sides. They cancel. Divide both sides by m, it's gone. This right here that I just finished, this 8.6, this is the centripetal acceleration. Boom, this problem's licked. I'm looking for the coefficient, 9.80. And then that was 8.6, I believe. So if I take 8.6 divided by 9.8, that should be my coefficient of friction, 0.878 or 0.87. That's the minimum coefficient. I could have more. I could have a larger coefficient, and I would still make the corner. But the moment it goes less than that, I'm not going to make the corner. Here's the other thing. This is where spoilers come into effect. Like, let's say your car had one of those really big old wings on the back. What that does, it's really, really neat how a spoiler works, because you're not adding physical mass to the car. What you're doing is you're adding downforce. And because you can add downforce, you have a larger normal force. So it's a way to make this bigger and not that bigger. Because you could, the more mass you add to something, you're going to have a bigger normal. So if you add them in equal portions, you make this mass bigger and normal bigger, you're not going to gain anything, because what you've gained you cancel out with how heavy it is. But if you can make something have a bigger normal without a bigger mass, now you can go around corners a lot quicker. And that's literally the whole science behind the wing. Same with banking corners. We'll get to more of that stuff, but like banked corners, all that stuff aids in going around corners much, much faster. So, just as a recap, why is an object moving in a circle at a constant speed? Because there's a force. Anytime you have a net force, then you have acceleration in that direction. How does it depend on the velocity and radius? The tighter your velocity, the tighter your radius, the bigger the centripetal acceleration. So the smaller the radius, the bigger the acceleration. The bigger the velocity, the bigger the acceleration. So it's directly related to the velocity and indirectly related to the radius. And that's why you kind of see the radius on the bottom and the velocity on the top here.